So a quick overview of what we're going to be looking at today. We're going to be giving a bit of an introduction into the OSI model, just a very nuts and bolts overview of it, just to get a basic understanding of what's going on. We're going to have a look at a basic copper and cable fiber basics, and then we'll talk about layer 1 testing very quickly. And then we're going to move into the main body of the presentation, looking at testing layers 2 through 4, common terminology you'll come across, common tests that you might have to undertake. We'll touch quickly on different test sets, and then towards the end of the presentation, we'll look at undertaking an RFC2544 and Y.1564 test on a VIAVI MTS 5800 test set. Okay, so the OSI model first up. So what is the OSI model? Well, basically it's a theoretical model which can be helped to use to understand and interpret how a network essentially operates and functions. And while we're looking at the OSI model, well, essentially it's utilized and pretty universally accepted worldwide as a 7-layer model, which can be used to describe how networks operate and function, and dictates and details what protocols are applied and utilized at different layers. Be aware that there's multiple models out there that can describe the same sort of principles, but the main reason we're looking at the OSI one is it's pretty heavily referenced when we talk about Ethernet testing. So today you'll hear me talk about undertaking testing on layer 1, or perhaps undertaking testing on layer 4, and these are really the key things that we need to identify and understand when I'm referencing back to the OSI model. So OSI model is essentially made up of 7 layers. So as mentioned today, we're going to be primarily looking at layers 1 through 4, and layers 1 through 4 are the physical layer, and that's got to do with the copper and fiber cabling itself. It's got to do with we'll then also look at the data link layer, which has to do with the framing of data. And today that's primarily going to be focused surrounding looking at MAC addresses and testing that sort of layer 2 and layer 3. Layer 3 is the network layer. So that's going to be looking at the IP addressing and routing of the packets of information. Layer 4, in layer 4 today, we're going to be looking at transport protocols, TCP, and testing that through what's called a true speed test. And we'll look at that towards the end of the webinar. And it's important to understand that on layer 4, TCP is actually responsible for quite a few different tasks, and probably one of the most important will be the identification of packet loss. And packet loss, and TCP looks at packet loss by monitoring what packets are transmitted and what packets are received, and identifying if there's any missing packets. And if there is missing packets of data, it organizes a retransmission of that data. So TCP is a very important protocol for ensuring good quality of experience for the end user. Today, we're not really going to touch on layers 5, 6, and 7 that much at all. Just be aware that layer 7 is essentially the layer that the end user will interact with. So if you're hypothetically looking at a website or writing an email, your function or working within the application layer. But when we talk about application layer, we're not talking about Mozilla Firefox or Google Chrome or applications like that. We're actually talking about the protocols behind those given computer programs. So HTTP or HTTPS as an example for when you're browsing the web, or maybe SMTP for when you're sending an email. The last slide I'm going to spend on the OSI model is just a bit of a quick example of essentially how the OSI model functions. And in this example, we're looking as if we're sending an email. So if we're sending an email in Outlook, we're creating an Outlook on your computer. Once we hit send, Outlook creates the email using a protocol called SMTP. Once we hit send, the packets of data start making their way down the OSI stack. So it goes from the application layer down into the presentation layer. And the presentation layer is essentially responsible for translating information, all those packets of data, into a way that both the receiving and source network devices understand. Next, the packets of information will start to move further down the stack into the session layer, where a session with a receiving mail server is started. Next, we're going to move into the transport layer, and this is where TCP is utilized to look at adding source and destination ports to the packets of information. Remembering that on this layer, TCP is also going to be looking for what packets are transmitted and what packets will ultimately be received on the far end. Next, the packets of information make their way down to the network layer. So this is where IP addresses are added to the packets of data to ensure correct routing. Down onto layer 2, MAC addresses are added, and then the information is finally transferred into the physical layer. So this is, as mentioned before, the physical copper or fiber cabling, and this enables the information to be carried from one given location to another. Once the information is received on the far end of your network, essentially the whole process is reversed, and the packets of data make their way up the OSI stack, where back on the application layer, your work colleague or whoever you sent the email to will get a notification of that an email has been received. So it's a very nuts and bolts description of how this OSI model functions and operates. For today's webinar, be aware that, obviously we're looking at layers 1 through 4, and the key takeaways you need to be aware of is that when we're talking about testing layer 1, we're talking about testing the actual physical copper or fiber interfaces. If we're talking about maybe testing layer 4, we're going to be looking at testing the performance of TCP and so forth. So we're going to refer to certain tests as a layer 2 test or a layer 3 test, and these are the layers that we're going to be referring to. Okay, so we talked about the OSI model. We're just going to quickly touch on copper and fiber cable basics. For copper cable basics, primarily in this day and age, you're going to be working with Cat 5, 6, or 7 cables. Be aware that there's Cat 8 cables are out there, but they're not widely utilized at the moment. And essentially, they're made up of twisted pairs of copper wires. Messages are carried along the copper wire by sending through smaller electric pulses along the wire. Now, the actual pairs of twisted wires, the reason they're twisted is that obviously when we send electricity through a cable, it creates a small electromagnetic field, and that electromagnetic field can create interference with adjacent wires and adjacent twisted pairs of wires. So by twisting them together, it can aid in essentially cancelling the electromagnetic field out between a pair of wires and improving the cable performance. The key differences between Cat 5, 6, 7, and 8 cables will be essentially the degree of shielding that's utilized in those cables, with Cat 6A, Cat 6, Cat 6A, Cat 7, and Cat 8 cables having different levels of shielding, which obviously increase the performance and bandwidth you can get out of a given cable. Fiber cable basics. For today's webinar, just be aware that there's two main types, single mode and multi-mode. Single mode has a much smaller core diameter than multi-mode, which has a much larger core diameter. Single mode, much better at carrying data over longer distances, as opposed to multi-mode, which is is more typically used on shorter runs. Why would people use multi-mode over single mode? Well, previously it was cheaper to manufacture, but that sort of benefit has fallen away over recent years with a reduction in manufacturing costs, and you're starting to see single mode fiber take over applications that were traditionally allocated towards multi-mode fiber. If you wanted to know more about fiber, feel free to get in touch. We ran a webinar a couple of months ago on sort of an introduction to fiber, and I'm happy to share any information with you from that if needed. So now we're going to talk about physical layer tests or layer 1 testing, and there's two main things that we can look at, and that's with copper for copper, it's copper certification tools, and with fiber, we've got fiber certification tools or the use of an OTDR. Copper certification tools are just going to be something like your VIAVI certified 10G or 40G test sets. These test sets come in pairs. One goes at either end of any given cable under test. Signals are passed between the two test sets, and then the remote test set takes readings on the performance of those signals to give you a quality and a report on that given cable under test. Key things to look at when you're undertaking testing with test sets like these is you need to be cognizant of what cables are you testing and what cables you want to be able to test in the future. So, if you're only doing Cat 5 and 6, you can look at getting hypothetically a certified 10G. If you want to do fiber or Cat 7, Cat 8 cables in the future, maybe you've got to look at a more advanced model like the 40G. For fiber certification tools, be aware that there's essentially two tiers of fiber certification, and which tier of certification you're using will be based upon your organization's requirements or your customers' reporting requirements. So a tier 2 solution is actually the more advanced of the two, and this will be done using a tool called an OTDR or optical time domain reflectometer, and that can be done using either a unidirectional test or a bidirectional test. Essentially, the difference is a unidirectional test, you've got an OTDR at one end of the fiber. Bidirectional OTDR test, you've got an OTDR at either end, which combine the traces to create one overall report for a given link. So OTDRs essentially show a visualization of the entire link, including event location, loss and reflectance, and so forth. It's a very comprehensive test set, and an OTDR, depending on the quality of your OTDR, can undertake a trace on a given fiber for over 100 kilometers, depending on its dynamic range. So it's a significantly more comprehensive test set than our certified product range, which will be the same tools that I talked about for the copper certification, but with the addition of fiber modules. And that's going to give you details on the length, the link loss, and the polarity. So that is if we're testing from A to B or B to A. So which way around we're undertaking testing on a given fiber. As mentioned, if you want any more details on fiber certification tools, let me know and I can forward you through some additional information, but that's sort of all we're going to cover for today. Just in terms of the certified test sets for fiber capability, these are the sort of fiber modules that you can look at getting to add to your capability if you want to increase from just copper testing capability to copper and fiber in the future. So that's sort of the real basics of layer 1 testing. We're just going to move into talking about testing layers 2 through 4 now. And before we get into too much detail on testing layers 2 through 4, there's a few definitions that we'll look at to make sure that everyone's on the same page when we start talking about different KPI measurements in the RFC2544 and Y.1564 tests later on in the presentation. So first up, we'll talk about latency. So latency is essentially the amount of time it takes packets of data to get from one location in your network to another location in your network. And ideally, you want it to be as close to zero as possible because you want as fast a connection as possible. Be aware that there are certain things limiting how fast latency can be. So as much as you want it as close to zero as possible, that's not always going to be the case. And it's limited, the first and foremost thing it's limited by is how fast the signal can travel through a given medium. So if you've got a fiber link between two network devices, the fastest or the shortest latency you can have will be dictated by how fast light can pass through that given piece of fiber between your two network locations. There's additional factors that will contribute to latency as well, and that's got to do with your network configuration, how many bottlenecks and so forth are throughout your network, which can all have negative impacts on your latency. Round trip delay, very similar to latency, and that's got to do with the amount of time it takes your packets of information to get from one network location to another one, and then that second network location transmitting a packets of information back, acknowledging receipt of the first packets of information. So essentially, it's the amount of time it takes packets of information to get from one location to another and back again. Packet loss. So I sort of mentioned this earlier when I was talking about TCP, and TCP is pretty important in the monitoring of packet loss. So packet loss refers to the number of packets that are transmitted from one location to another that fail to be received. And this is measured or quantified by looking and capturing traffic on both ends of your given network link, and then identifying which ones are missing or which packets, and then which packets need to be retransmitted. And as I mentioned before, Transmission Control Protocol, or TCP, is responsible for this. So TCP detects packet loss and then performs the retransmission, which gives you the reliable messaging. So if you're working on a network that's experiencing a high amount of packet loss, that's going to be reflected in poor quality of experience for the user. So if you're theoretically streaming a video and your network's experiencing a high degree of packet loss, you're going to see a lot of buffering in that video as TCP continually requests a retransmission of given packets. Now, an important capability of TCP with regards to packet loss is that TCP can intentionally reduce the throughput of a given Ethernet link. Now, the reason it does that is if you've got a given link and it's operating pretty close to capacity where you're getting a high number of packets of data that are lost, it's got to have to continually request retransmission of those lost packets. And those lost packets are then being added to the amount of traffic in that given link as well. And when you start increasing that amount of traffic through that link to a point that it's at its capacity, then that can contribute to more packets of data loss, and then there's more retransmissions requested, and it can sort of snowball and get worse and worse. So by TCP throttling the throughput and reducing the amount of packets that come through that link, it actually starts to reduce the amount of packets that are lost, and in turn improving the performance of a given link. So TCP is very important in terms of packet loss and monitoring it, and giving a good quality of experience to the end user, remembering that this is something that happens on layer 4. And we'll talk about testing layer 4 further on. Jitter. So we talked about latency earlier. Jitter is essentially the variation in latency or the variation in time delay for packets which are being sent over a network. So hypothetically, you could have a network with latency of 2 milliseconds, and that's essentially the amount of time it takes packets of data to get from one location to another is 2 milliseconds. And if it's consistently 2 milliseconds all the time, which is very, very unlikely, then your jitter would be 0. You would have no jitter at all. In reality, you're probably going to have some variation in that latency time created by bottlenecks, varying amounts of packets of data moving across a network and so forth. And that variation, that latency time, is called jitter. If you've got a latency of some packets information at 2 milliseconds and some packets of data coming across at 5 milliseconds, then your spread or your jitter buffer is 3 milliseconds. So that's the difference between the fastest packet of data and the slowest packet of data. Remembering that your effective latency is only as quick as your slowest packet of data. So here we've just got effective latency, and that's at the top end of the curve. So in that example before of some packets coming in at 2 milliseconds and some coming in at 5 milliseconds, your effective latency is 5 milliseconds, and your jitter buffer is 3 milliseconds. So the difference between the two. But just for today's presentation, just understand that jitter is essentially the variation in your latency times. Next, we're going to quickly touch on throughput and bandwidth. And these are sometimes terminology that are used interchangeably, and they really shouldn't be. So first up, we'll chat about bandwidth. And bandwidth is essentially a measure of capacity of a given link. And it's measured in bits per second. So that could be megabits per second or gigabits per second. And think of it essentially as how big the link is, or what's the capacity of the link, how big is your pipe. And then throughput is defined in terms of the actual amount of data or the number of packets that can be delivered through that given link in a predetermined time frame. So hypothetically, we could have a 1 gigabit link capable of 1 gigabit per second, and the actual throughput may only be 2 or 3 megabits per second if we're only using it to, say, transfer timing packets from a time server into your network. So it could be very small. And when we have a very small throughput in a link that's got a high bandwidth, we have very few problems typically. The opposite to that is if we've got a 1 gigabit per second bandwidth and we're operating, or the throughput is consistently up at that 1 gigabit threshold, then that's where we can start experiencing a lot of issues. And that's because any small, tiny issue in the network is then exaggerated. Not to mention when we start talking about retransmissions of packets that we just talked about through packet loss and TCP, those retransmissions will start to get to a point where we're exceeding the bandwidth of the given link and creating more and more issues. So having a low throughput relevant to bandwidth is a key to improving network performance. And the final two bits of terminology that we'll talk about today are shaping and policing. So traffic shaping is essentially an intelligent network buffering system where the network device shapes the traffic in accordance to the CIR. So the CIR is your committed information rate, and that's an agreed bandwidth that you've agreed to upon in your service level agreement between a network provider and a customer. So hypothetically, a network provider and a customer could agree in their service level agreement to a 1 gigabit per second link. And when I talk about the CIR, that's referred to here at the traffic rate. So that's our rate that we've agreed to between our network provider and our customer, and that's the rate that we've tested to and make sure that the link operates properly up to. And we'll talk about that later when we talk about specifically Y.1564 tests. Now, if shaping hasn't occurred on data, on packets of data coming through the network, it can often burst as in this left-hand picture. And we can see that every time it bursts above the committed information rate, this is areas where the performance of the link hasn't been monitored. And that's going to create a lot of issues in terms of packet loss and so forth. And when we talk about packet loss, then that creates issues with the retransmission of packets and so forth that I just mentioned earlier. So by shaping the data like this, we actually continually keep that rate just under the committed information rate. And that obviously leads to lower degrees of packet loss, lower network issues, lower packet queuing and so forth, which will obviously give us a much better network performance and end user experience. So this is something that's tested for on layer 4 as well. Now, policing essentially prevents users from getting more bandwidth than they're allocated. And it does this by discarding excess packets. So in the same example here, data, or bursting packets of data, every time it would exceed the committed information rate, those packets of data are discarded. And the main reason for that is if we go back to the example of the service level agreement that we've agreed to is a 1 gigabit per second link, we don't want our customer to have 2 gigabit potential speed capacity because they're not paying for that essentially. So policing discards those excess packets to keep it underneath the committed information rate. And there's also benefits to improving network performance by doing so as well. But that's the basics for shaping and policing. Now, before we get on to too much in-depth talking about testing, I just wanted to have one slide on talking about common tooling. And I'm not going to go into a whole range of different bits and pieces about each individual test set because quite frankly, there's thousands of different options and configurations that you could have to undertake your testing requirements. The key things you need to be cognizant of when you're thinking about undertaking testing is that one, what sort of speeds are you looking at? Are you looking at 1 gigabit per second, 10 gigabits per second, 100, 400 gigabits per second? There's different options to meet your requirements. Second of all, what sort of tests are you undertaking? So if you're in the utility industry, maybe C3794. If you're just doing commissioning basic single service Ethernet links, maybe RFC2544 and so on. And then in a lot of these tests for especially commissioning new Ethernet links, you're also going to require a loopback device. So do you want to get two of your identical units, one with a loopback option, or do you want to look at a dedicated loopback device, such as the network companion? These are all different bits and pieces that you need to consider when you're looking at investing in new test sets or new tooling. The other thing I would probably encourage you thinking about is not only what tests and capacity do you need for right now, but maybe look at 12, 24 months in the future. What capacity are you going to need in the future? And I only say that because technology is increasing at such an incredible rate that it's probably worth investing in the next test set up and then essentially locking it to the lowest speeds or lower capacity you need at the time, which may be a little bit more expensive than getting a lower unit right now, but it protects you for the future and you can just software unlock it as you move forward, which will give you added capability and reduced capital expenditure in the coming years. But if you need any assistance working through different test sets and so forth, feel free to get in touch with us and we can help you through it. So common tests undertaken on Ethernet links. So for today's presentation, when I'm talking about common tests, I'm going to be talking about all tests undertaken on VIAVI units, and for tests in particular, when we talk about testing later on, I'm going to be doing it on a VIAVI MTS 5800. So for today, we're going to look at two main service activation tests, and that's going to be RFC2544 or your Y.1564 test. Now, the difference between these two is that an RFC2544 will be utilized on a single service or a single stream service, whereas your Y.1564 will be used on a multiple service link. So in a single service link, you'll have a link that's only used for data or only used for voice, whereas your multiple class of service will be used for voice, video, and data, as an example on the one link. Now, the workflow we're going to be looking at today for both tests will be undertaking what's called a Quick Check test, which is a VIAVI painted test to essentially give you a basic connectivity test, and we'll talk about that on the next slide. We'll then run through either an RFC2544 or Y.1564 test, depending on if we've got a single service or a multiple class of service link. And then we'll talk about looking at our customer quality of experience on a layer 4 true speed test, so the RFC2544 true speed test. So we've got our workflow up here in the top right corner, and the first thing we're going to do is our Quick Check test. So this is integrated on VIAVI units into both the RFC2544 and Y.1564 tests. Essentially, this test happens almost instantaneously once you finish the configuration, and it does three main things. And the first one is it correctly auto-negotiates some of the settings that you've put in. So it confirms the settings you've put in are most likely going to give you a good result and a good test. Next, it'll automatically check for connectivity and serviceability with the loopback device at the far end, and then it'll perform a very quick throughput test at the maximum rate that the test set is capable of for that given option. So if you've selected, even if you've got a 100 gigabit capable test set, if you've chosen the 1 gigabit test, it'll do a quick throughput test at 1 gigabit per second, even if the committed information rate you're going to be testing at is 200 megabits per second, just to test the serviceability of the line and to test the serviceability of the loopback device. Now, why is this important? Why wouldn't you just think, well, we'll just start the RFC2544 test and it'll tell us if there's an issue? Well, yes, it will, but a Quick Check test takes, literally a couple of seconds to undertake, whereas the enhanced the RFC2544 test or Y.1564 test can take a considerable amount of time depending on how you're testing it. So RFC2544, depending on what you're testing, what bandwidths you're testing and so forth, can take up to, an hour to 2 hours depending on your configuration. At its absolute quickest, it might be 30 minutes. So, that's going to take you 30 minutes before you realize that you've got a configuration error in with this Quick Check test. Likewise with Y.1564 test, part 2 of the Y.1564 test can have a soak time up to 24 hours. So you don't want to be coming the next day to come in and go, oh, there was a connectivity issue or an issue with a loopback device straight away. So that's what this test looks to prevent. All right, so moving on, looking at our layer 2 or layer 3 RFC2544 test. As mentioned, this is a widely used service activation test for Ethernet and IP services for single services only. So that is links that you'd only use for data, or it's only be used for voice. And you might utilize that for something if you're commissioning a new microwave link or something along those lines, where it's only got one type of service across your Ethernet link. And what we're going to be measuring here is pretty much those KPIs that we described before and went through definition before. So throughput, latency, frame loss, packet jitter, and bursting. So committed burst size as well. And then once you complete your report, the test set will automatically produce a report, which you can be handed up to management or senior engineers or whoever may require it. So how does an RFC2544 test actually work? Well, as mentioned, you've got your local unit here on the left, and this is the one that we'd be undertaking our testing on. We've then got it connected to our link under test, and on the far end of that link, we've got a loopback device, and that loopback device could be one of dozens of different options. The only limitation you have for your loopback device is primarily that it has the same capacity as the link that you're wanting to test. So if you're wanting to test it at 1 gigabit bandwidth, then you will need a device on the far end capable of that particular speed or bandwidth. So if you're testing a 1 gigabit link, you'll need a 1 gigabit suitable device on the far end. If you're connecting a 100 gigabit link, you'll need a 100 gigabit suitable device on the far end. That can be, like I mentioned, that could be a whole range of things. It doesn't have to be a portable unit. You could have a permanent fixture NID style device, such as those from a CDN, perhaps an SFP with loopback capability and so forth. So there's a whole range of options you can go from there. In terms of how the test actually starts and operates, the first thing we're going to do, as we mentioned before, was the Quick Check test. And in that Quick Check test, essentially that small message is sent up to the loopback device. The loopback device receives that message and then sends an acknowledgement of that message back, saying that configuration settings are good and so forth. And in that process, a quick throughput test is done as well to the maximum speed of the test that you've selected to undertake. Once that Quick Check test is done, Next, the RFC2544 test starts, and that's where actual test packets, including sequence numbers and timestamps, are released from the local test set, sent up to the loopback device. Depending on how you've got your loopback device configured, most likely it will just reflect the test packets straight back to the local device, only switching the MAC addresses on layer 2. And when we talk about testing on layer 3, it will also switch the IP addresses of the source and destination IP devices. And that's just to ensure correct routing of the information back to the local unit. And that's essentially how an RFC2544 test is done, remembering that when the packets arrive back at the local unit, depending on how you've configured your test, it will take specific measurements either at the local device or at the loopback device. And I'll talk about that shortly when we talk about configuring our RFC2544 test on our 5800. In terms of other options for loopback, you can undertake testing with using what's called a hard loopback, and that's a simple, can be as simple as a piece of fiber loopback on itself. And that's in that situation, the test packets are simply sent up with a timestamp, and then the test packets are then received back at the local unit with the same timestamp with performance characteristics and KPIs measured appropriately. Remember that for the physical loopback, that your network has to be suitably configured for that. So if you've got a lot of routers and switches, you're not going to be able to undertake testing effectively with a hard loopback device. Next slide, I just wanted to talk about the enhanced RFC2544 test, which is a patented test from VIAVI. And the enhanced RFC2544 covers the same KPIs as a traditional RFC2544 test, but one of the key benefits is it's significantly reduced testing time. And its reduced testing time comes about by, rather than undertaking tests one after the other, so a throughput test, then a latency test, a frame loss test, and so forth, it actually conducts these tests simultaneously. And what does that mean for the end user? Well, it means a significant reduction in testing time. So we can see here on a traditional RFC2544 test for throughput, latency, frame loss, and so forth, you could be looking at up to 104 minutes, but with the enhanced RFC2544, you get that down to about 33 minutes. And I mean, that's a significant improvement. And in terms of business operations, that's a huge time saving in terms of man hours, especially if that's only one use. Imagine over the life of your test set, if you're doing, a couple of hundred of these a year, that's a huge amount of time you're saving. So definitely a worthwhile investment. So that's RFC2544. We're now going to touch on Y.1564, which is a newer industry standard for single and multiple service Ethernet and IP service activation tests. So the multiple service is the key difference between Y.1564 and RFC2544. And once again, we're going to be looking at measuring key performance indicators and bandwidth profile, a lot similar to the KPI definitions that we talked about before. So first up, we're going to be talking about measuring bandwidth profiles for the committed information rate. As mentioned, this was something that's going to be dictated in your service level agreement, and your excess information rate. So this will be a rate just above your committed information rate. Your frame delay or latency, your frame delay variation, very similar to jitter. Your frame loss rate, once again, we're going to talk about committed burst sizes, and Y.1564 also looks at measuring and testing for policing. So the Y.1564 test is broken up into two main parts. So part one is we're looking at a single service configuration test. So we're looking at only one service only on a link that's got multiple services on it. In part one, we're going to be looking at the performance up to and including the committed information rate. So in this first part, we're going to be looking at breaking, if we've agreed to a committed information rate in our service level agreement of 1 gigabit per second, we want to test that committed information rate at a number of levels below 1 gigabit per second and then at 1 gigabit per second. So hypothetically, at steps of 100 megabits per second, so 100 megabits per second, 200 megabits, 300 megabits, and so forth, for delay, jitter, frame loss, which are dictated in our service level agreement. So your service level agreement will have acceptable passing standards for each of these parameters. At each step, we want to be testing it for a given amount of time, and this is customizable up depending on your requirements, your network testing best practices and so forth. So that'll be determined by the end user and is configurable in your test set. Once we've tested at each of those given steps up to and including the committed information rate, so in this case 1 gigabit per second, we're actually going to test at rates above that as well. And that's testing at a rate called the excess information rate. And at the excess information rate level, we're testing beyond the service level agreement. And because we're testing beyond that, the throughput and serviceability or passing levels, we're only looking to get indication. We're not looking to actually have to pass against the service level agreement because we're operating outside those parameters. Above the excess information rate, we want to then check for policing. And that's those discarding of packets I talked about before. And that's to ensure that a customer isn't getting a service they're not paying for as one of the main reasons. All right, so that's part one of the service activation test. Next, the Y.1564 moves on to a part two. And in part two, we're looking at testing data on each of the multiple services simultaneously at their committed information rate and looking to measure KPIs for each service caused by the impact of each other service. So hypothetically, we want to make sure that in a given link, if we're operating the data aspect of that link at its committed information rate, whatever that may be, we want to see what sort of impact is that having on the video link. Or if we're operating that video link at its committed information rate, what sort of impact is that having on the voice link and the data link? So these are all the sorts of things we want to see how one service is impacting the other services that share that link. And we're looking at the same parameters or KPIs as we did in the part one test. So frame delay variation, frame loss rate, all of which will be dictated in your SLA. In terms of testing time for this, this is done over a mid to long time period. So depending on your testing requirements and how many services or concurrent services you have on one link will determine how long that test will be. But it wouldn't be uncommon to see a test go for 3 or 4 hours up to 24 hours, depending on the testing that you're undertaking. Okay, so we've talked about Quick Check, we've talked about layer 2 and 3, RFC2544 and Y.1564 tests, and now we're moving on to a layer 4 true speed testing. Layer 4 true speed testing is very quick and very easy. And essentially what you're looking to do on this test is pre-qualify the customer experience. So you want to test that the customer is actually getting the speed that's agreed upon in their SLA. And we want to look at testing TCP. So we're looking at TCP efficiency, actual application throughput. And then as mentioned before, we're also looking at measuring the performance of shaping of data and so forth. Aspects like round trip delay and round trip time and so forth. So it's very simple. And essentially to do this, you walk out to your customer's site or premises with your test set, connect your test set up, hit layer 4 true speed test. And essentially it'll just spit out these parameters off your given link. So it's very, very simple and easy to test for. So when we're talking about industry best practices, what does that mean? Well, when we're looking for network configuration issues, the test that we want to undertake is the RFC2544 and Y.1564. Once again, depending on if it's a single service or a multiple service link. What we're going to be looking at is measuring those KPIs that we talked about. And the types of problems you're going to identify with your RFC2544 test or Y.1564 test has to do with your physical equipment configuration issues. And the reason you want to undertake these tests primarily is to reduce the number of issues you have in your network and reduce the number of repair tickets you have. Because every time you have to go out to repair a ticket, that could be a truck roll, that's going to obviously cost business money and obviously time and hassle. So we want to make sure that when we commission a link, we do it properly using the correct tests and test equipment. In comparison, if your customer rings up or an end user rings up complaining about a slow or a poor quality of experience, then we're going to be looking at utilizing a layer 4 true speed test. So that's your RFC2544. And what we're going to measure in there is essentially your application throughput. So how much speed or bandwidth are they actually getting on the far end? And then the type of problem you're going to identify is, as mentioned, your customer experience or quality of experience. And the main benefit here is you can eliminate finger pointing. So if you go out to your customer's premises, undertake a layer 4 true speed test, you know that the committed information rate on their SLA is 1 gigabit per second. And you connect up your test set and say, and show them, hey, you're getting 1 gigabit per second at the end of this given link, then that means that they need to look internally at their own network configuration and so forth. So it's the problem lies with them as opposed to you. So that's what the main thing you want to identify when you're troubleshooting for customer experience problems. Okay, so we sort of covered all the tests from layers 1 through 4, and now we're just going to quickly run through how to undertake some of these tests on the MTS 5800. So the first test we're going to look at undertaking is our RFC2544 test. And as mentioned before, the RFC2544 test will require a local unit and a loopback device. So we've got our local unit connected to one side of our network, and then on the other side of our network, we've got our remote loopback unit. And as mentioned, this loopback device could be any number of things, whether it's an identical MTS 5800 with a loopback option, our network companion, an SFP with loopback capability, or maybe a NID device such as the CDN Metro NID variants. When we start up our 5800, this is the screen we're going to be shown to. These options here are going to be our favorite tests. So these are the tests that you would have done the most previously, or tests that you've pinned and saved. So the one we're going to look at today is the 10-100-1000 layer 2 traffic RFC2544. Now, if you don't have it pinned to the home screen, you can find it in the side menu here. Just a quick note that if you currently have a 5800, it might look a little bit different to our one in terms of menu options. Obviously, this was done on the Vicom demo unit, so we've got every option you could possibly get on a 5800 just about. So you might be missing some of these menus. If you wanted any tests that you can see here, get in touch and we can look at getting them added to your unit. That's not a problem at all. Now, because we're talking about layer 2 on the Ethernet, layer 2 Ethernet testing, then we're going to click on the Ethernet menu down the side here. And the first sub menu will be to choose your speed that you want to test at. Today we're only going 10-100-1000, and then we're going to go to RFC254 up here. And this is where you can choose whether you're doing a layer 2, layer 3, or layer 4 RFC2544 test, either IPv4, which is standard for layer 3 and 4 on the 5800, or you can get IPv6 as a purchased option as well. But today we're only going to do layer 2 traffic. So we click on layer 2 traffic. When we open it, it opens up the enhanced RFC2544 wizard. So it's a wizard to enable easy access, easy configuration, and make it easier for people that don't do a comprehensive or a lot of Ethernet testing and so forth. So the first thing we're going to do is start a new configuration, noting that if you're doing a lot of repeat tests, you can save configurations, so you can go straight to the test screen later on. But for today, we're going to start a new configuration. So this first screen talks about how we want to look at looping back the data if we want to loop back the packets of data if we want to loop it back at all. So the three options are symmetric. So this is where downstream and upstream throughputs are the same. So the data going up will be the exact same as the data coming back. If we're using not a hard loopback device on the far end, the only difference will be that the MAC addresses will be changed. We can look at doing asymmetric testing where downstream and upstream throughputs are different. In order to undertake asymmetric testing, we're going to need a similar unit on the far end as the loopback device. So that might be a second MTS 5800. And in that case, we're going to be generating traffic at the local unit. It's going to be received at the loopback unit. And then that loopback device will generate new traffic and send it back to the local unit, which will undertake separate measurements as well. We've also got an option for unidirectional testing, remembering that if we select unidirectional testing, you're not going to be able to undertake some measurements such as round trip delay or round trip time, because obviously the packets of data aren't going to be coming back to the local unit. And then the measurements, we can look at taking them locally only, which will be on the test set that you're actually working on, or we can look at taking measurements on your downstream and upstream device. Once again, if you're doing downstream and upstream measurements, you're going to need a suitably a suitable unit for your loopback device, whether that's another MTS 5800 or maybe an MTS 6000 or some sort of capable unit on the far end. Next, we're going to talk about network settings. The only real menu you'll need to look at on this particular screen will be encapsulation mode. In this case, we've got VLAN selected. Because we've got VLAN selected, you also need to put in an appropriate VLAN ID. And then just hitting next down the bottom. This screen is a little bit different for layer 3 tests. So we were talking about a layer 2 test just before. This is one of the main differences for a layer 3 RFC2544 test. And that is that we need to include the source and destination IP addresses. So our source IP address is for the local test set that we're using, and that'll be pre-populated. And if you can then insert your destination IP address, which can be obtained off the FAR unit when you're configuring the test. So you can just input that there in the textbook, in the text box, and then you can undertake a quick ping test to make sure that it's correct. But moving back to layer 2 testing, there are options to undertake pre-made configuration templates. You can create your own template if you want. If you select yes, there's just a drop-down box here with a whole range of different templates that you can utilize with the template configuration listed below. For today's example, though, we're going to click no. If you do end up using a template and hit next, you can jump straight through to the quick check screen, which is the immediate screen before you start your final test. But for today, we're going to go with no, and we're going to manually configure it and hit next. The next screen is our test that we want to actually undertake for our RFC2544. Now, a lot of people I've talked to have the mentality of, oh, we're undertaking a test anyway, let's just do them all whilst we're here. Yes, that is possible. My recommendation is not to, because it can add considerable amounts of time to your test. Going through oops, sorry about that. Yeah, so you can add, by selecting additional tests, you can add considerable amounts of time to your test time. So my recommendation is only undertake the tests that are absolutely required by your testing procedure or your network requirements. Moving along, next we're going to talk about bandwidth, and the max bandwidth you're going to be undertaking testing on for your RFC2544 test is going to be your committed information rate. So in this case, we've set it to 200 megabits per second. On this next screen, this is where you get to choose between your RFC2544 standard test or your VIAVI enhanced. Remembering that VIAVI enhanced will essentially cut down your testing time. So that's where you get to choose between those two. And on the next screen, the only real option you need to worry about is your bandwidth granularity of your data. Once again, that's determined by your network testing requirements. The next screen is probably one of the most important, and this is where you actually configure the pass and fail results for your RFC2544 test. So as mentioned, throughput threshold, you're probably going to set that to your committed information rate, as we did before, which was 200 megabits per second for this example. And then you can set your throughput frame loss tolerance, latency, packet jitter, passing standards, and so forth as well. If you don't want any particular measurement to be included in your pass or fail results, you can simply uncheck the text, unselect the option. And then we'll hit next. Next, just the saving screen, a whole range of different options to save it for. You can save it on the hard drive of the MTS 5800, upload it directly to the cloud with Strata Sync, or maybe to a USB or portable hard drive as required. This next screen is where we want to start to run our test. If you want to go back and change your configuration, there's a couple of buttons here to undertake it, but for now, we're just going to run our test. This is the quick check screen I was talking about before. So this is immediately before we start our actual RFC2544 test, and we're checking those main things. So that first one was that throughput check. So remember how I mentioned we're only testing at 200 megabits per second? Well, we've done a measured throughput check at 1 gigabit per second to check serviceability of both the local unit and the loopback device. and the maximum capacity of the given link. We've also checked that the remote loopback device is an active loopback device as opposed to something like a hard loopback device or hard loop. And we can see it's green and ready to go. Auto negotiation settings are on, so settings have been configured appropriately for the loopback device. And we'll notice that if we have a hard loopback, that won't be applicable. And then we can see the local port is good to go as well. So once all those three things are green and good to go, we can hit start on our test and we'll be taken to the next screen, which is our RFC2544 test screen. As mentioned, RFC2544 test can actually go for an extended period of time. So when the test is running, this is a screen that we'll have, but instead of seeing the green ticks in the appropriate boxes, we'll have the blue hash that it's running. If we want to blow up and see in-depth information for how a particular test is going, we can just click on the magnifying glass and it'll bring up an expanded screen of what's exactly going on in that particular test at that point in time. Obviously, if we get a fail for any aspect of our test, we'll get the red check mark, red cross, and we'll be able to identify what's gone exactly wrong in that particular test by clicking on the magnifying glass again. But in this case, it's all passed and it's all good, so we'll hit next and move on to our create report screen. So we can hit create report here. There's a number of different options you can choose from your report, whether it's a CSV file, PDF. I think there was 5 different options that you can choose from, so you can configure it however you would like to. And in this final screen, we're just going to put in details about the test, who undertook the test, where you did it, and so forth. You can even include your company logo if you wanted to do that to make it look professional before you send it off. So once we create a report, we'll hit next. And this is a sort of a summary or an example of the report, what it looks like. So RFC2544 test report is around about 8 to 10 pages long, depending on exactly what you've tested. We can see page 1 is essentially everything's passed or what's failed. We've got a summary of what you've actually done. So the tests that you've used, who's done it, where was the test done, when it was done, and so forth. And then the following pages are tabulated data and graphs of each particular test. So throughput and latency, frame loss, and so forth. And as mentioned, the data comes in both graphs and in tabulated form, so you can get all the information you require. So that was RFC2544. Now we'll just jump onto layer 2, Y.1564. Similar physical setup in terms of you require a local unit, a loopback device, so I won't go over that again. Once again, we jump into our 5800, and in our menu screen, we're back in the Ethernet menu, once again choosing our speed, this time in Y.1564. And we can see here that we've got a layer 2 or layer 3 options. Once again, layer 2 for single stream, so single service activation, which we'll go through today just because it's a little bit quicker. Or you could go into multiple streams, which is just below. So that's so instead of just testing a link that's got just voice on it or just video on it, we can do multiple streams on which would have your voice, video, and data, or voice, video, data, gaming, and so forth. And then we can see down here that we can undertake similar tests for layer 3 IPv4 or IPv6 for both single and multiple streams. As I mentioned before, if you're looking for IPv6 capability, let me know, because that's an additional option for your 5800. So today we jump into layer 2 traffic, single stream. We're going to appear in a very similar wizard. Notice that this time we are now in what's called SAM complete. So not the enhanced RFC2544 wizard. And we're going to start a new configuration. Once again, we're going to choose symmetric and loopback for this particular test, but you can configure it as required for your test. This is the first screen where we're starting to move away from the same screens that was in the RFC2544 test. And this screen will be slightly different when you're undertaking multiple services, as you'll need to configure each particular service you're undertaking testing on. So this first box here, we want to configure our triple play. And here you can select your type of service that you're going to be testing. And as mentioned, if you've got multiple services, whether that's 3, 4, or 5, you will need to select what sort of service you're testing on each one of those boxes for each particular service. Next, moving along, we're looking at inputting our service level agreement details into the test set so we can test against them. So the first screen has to do with inserting our committed information rate from our service level agreement, and then our excess information rate and our maximum line rate as well. Now this is the excess information rate and maximum line rate are given in a format of plus so many megabits per second above the committed information rate. So we can see in this example, we're going +0. So that means we're testing those excess information rates at the committed information rate. And likewise, because we're putting our maximum information rate at the same level as our committed information rate, any packets of data that will be above the committed information rate, we will discard. Well, we're testing for discarding of those packets above 19 megabits per second. And we want to make sure that if we're testing for policing, we check this policing checkbox over here. Clicking next, this screen is where we look at including our pass and fail measurements from our service level agreement into the test set so we can measure against them in our part 1 and part 2 tests. Next, we're looking at configuring part 1 and part 2. So here is where we get to configure our number of steps at a rate below the committed information rate. So those steps I talked about before, this is where you get to choose how many steps you want to take. You can have as many steps as you like, and you can configure the duration for each particular step as you like as well. Remembering that if you start increasing the number of steps and increasing the duration of your test time of each individual step, the compounding impact on your total test time grows considerably. To break down those particular steps at different intervals, you can click the advanced setting here and configure each percentage at where those steps occur. So if you're doing that 1 gigabit per second link we talked about before and want it to happen at 100 megabit intervals, you would configure this to 10 steps and then change these percentages to 10% each, as an example. And these percentages don't need to be uniform either. So you could have a 25% step, a 50% step, and then it could go up in 10% intervals up to 100% as an example. For part 2 of the test, the only thing we really need to test or change is your test duration. So whether that's 5 minutes, 3 hours, 24 hours, whatever you want to change it to, that's in this box here. For this particular example, remember we're only doing a single service test. So because we're only doing a single service test, the service performance aspect of the Y.1564 can be quite a short period of time. Whereas if we had 4 or 5 services, and especially if we had 4 or 5 services on a much higher bandwidth, then that duration would need to be considerably longer. So just moving along, once again, save screen, can save the results however you like, and whether that's in the cloud or on a hard drive, and then we're going to run our test. This next screen, we can just choose if we're undertaking part 1 or part 2 testing. And then if we want to do an optional throughput test for RFC2544, we can do that as well, remembering we need to insert the committed information rate in our max line rate. Next, the Quick Check screen again. This time we're testing with a hard loop and we're testing for the serviceability of the local port, remembering that because we've got a hard loop, as I mentioned before, there's no requirement to test the auto negotiation settings of the Loopback device because it has none. So it's just a hard loop, it's just a piece of fiber or a piece of cable looping back on itself. Next screen is our Y.1564 test screen. So this will be the screen that the test set waits on whilst your test is being completed. We've got the same legend of codes essentially for when the test is being undertaken or not. And once again, we can click on the magnifying glass to blow up any in-depth detail that we might want to see about any particular test or service. Once again, moving along, same report configuration screen, can insert your logo as needed. And we pull up a report for your Y.1564 test. Now, a Y.1564 test report is quite in-depth. Depending on how many services you undertake, it can be quite detailed and quite long. So I think for this one, which was 5 services, it was about 20 odd pages long. Each page 1 has basically a summary of what's going on and has a test summary as well. So where the test was undertaken, when it was taken, and all the configuration settings used. For each individual service, you will then get a 1 or 2 page summary. And then you also get in-depth reporting on how each service has impacted each other service in terms of when it was operating at committed information rate, what the KPIs for each other service were. And then you also get that data in a bit of a tabulated form as well. Okay, so that more or less concludes this morning's presentation on Introduction to Ethernet Testing. If you guys had any questions, feel free to let me know and I'll be more than happy to answer them. If not, thanks for joining us this morning and we can go from there.
Excellent. Thank you.
No worries. Thanks for your time. Thanks for your time this morning.
Yeah, well done, Harry. That was great. Thanks, mate.
No stress. If you got any questions, if you think of any questions at a later date, feel free to send us an email or give us a buzz and we can go from there.
Thanks, Harry. Have a good day.
Thank you, Harry.
Thank you. Thanks for your time.